Another next interesting question from a past paper is a guitar string is 90 centimeters long and has a mass of 3.6 grams. The distance from the bridge to the support post is L is equal to 62 centimeters, and the string is under the tension of 520 Newton. What is the frequency of the second overtone? Second overtone. Now, this question is bit tricky because you have got two lengths, and you start thinking to say, okay, why do we have two lengths? Now, this 90 centimeters is the length of the string of the guitar, meaning this length I can use it to find what? I can use it to find the linear density. What do I mean? When we're talking about the fundamental frequency or the overtone, overtone is the same as the fundamental frequency or the harmonic. So they can say the second overtone or the second harmonic or the second fundamental frequency. Okay? Now, when we're talking about the second fundamental frequency, just know that the number of loop is equal to 2. The number of loop in this case, when we're talking about the normal standing wave, it is the same as the antinode. Okay? So in this case, what I'm going to do is, if I'm finding the second overtone, what we should know is we're going to have something like this. If n is equal to 2, meaning that L will be equal to n divided by 2 times lambda n. Now n is equal to 2, but I want us first to derive the formula. Okay, so I can make lambda as a subject of formula here, or we know that V is equal to the frequency. Now in this case, it's going to be the frequency n, which we don't know. Which overtone are we talking about? We are talking about n is equal to 2, but for now I'll just say Fn, then lambda n. Make F as a subject of formula. So divide both sides by lambda. V will be divided by this. So we'll end up having this. We'll have V, then lambda. Here now I can make lambda as a subject of formula because I have this L. Now this L which we're talking about here, it is this L. Because 90 centimeters is the one I'm going to use to find the linear density, because I know that the velocity, the speed of sound in a string, or the speed of wave on a string, is given by the force divided by the linear density. Now the linear density is the mass divided by the length. Now this length is 90 centimeters because it's the length of the string of the guitar, but we have the mass. So now here I'm going to make lambda as a subject of formula. So it's going to be lambda n is equal to 2L. Now I have got n, sorry, because this is n. Let's divide both sides by n, even here by n. These will cancel. Lambda n will be equal to 2L divided by n. So we replace lambda with the 2L over n. So I'll say 2L over n. I can get rid of this. So I'll end up having the fundamental frequency to be V divided by 2L divided by n. Then it's the same as V times n divided by 2L. Then this is the same as NV divided by 2L. Now this is the formula I want us to use. So V is given by the square root of, I don't have V, but I have the tension force and also the mass and the length of the guitar, the string of the guitar. So I can go ahead and now say this Fn is going to be n divided by 2L times V, where V is the square root of, so I'll say n 2L, V is the square root of the tension force divided by mu. Now let's go ahead and find mu. Okay, in a case where you have been given the first fundamental frequency, just here before I go any further, we are saying Fn is equal to n over 2L times V on top there. Okay, if n is equal to 1, what we need to understand is that if n is equal to 1, we'll have 1 times v is v over 2l, meaning that I can write this as n open brackets v over 2l. I know that v over 2l is the first fundamental frequency. So another formula for fundamental frequency can be given by this, n times the first fundamental frequency. This is also very important. Another formula which you need to know is that one. Then another one is the same one, where you have v, nv divided by 2l. So these are the main three formulas which you need to know under fundamental frequency. So let's go ahead and now find the answers. So let's plug in the values, but first let's find the linear density. We are saying that linear density is given by the mass. Now the mass in this case is 3.6. I'm going to convert this 3.6 divided by 1000, which is going to be 0.0036. Let's divide this by the length. The length is in centimeters, 90 centimeters. We divide it by 100 to convert it to meters, which is 0.9. So my linear density is going to be 0.0036, 0.0036 divided by 0.9. That is 0.004. Now it's kg per meter, because mass is in kgs. Then mass is in kgs, and the length is in meters. That's why it's kg per meter. Okay. So now that we have the linear density, we can go ahead and find we know that we are finding the second overtone. N is equal to 2. So where there is n, we will put 2. So I'll say f2, n is equal to 2. The length now, the length which we are talking about down here is now this one, which is 62 centimeters. So I'll say 62 divided by 100, which is 0.62. Then this times the tension force is 512. The linear density is 0.004, just like that. So the second overtone is going to be, I think the best thing to work out to do this, I can just say 2 divided by open brackets, then 2 times 0.62. Okay, so the answer I'm getting 1.6129. I'm not going to round it off, okay, because I want to get the accurate answer. Then times, now what is 512 divided by 0.004? Then the square root of this, which is I'm getting 360, sorry. I'm getting 360.55. We have 35, then 275. Then now I multiply these two. So the second overtone will be equal to 360.5551275 times 1.61290326. So I'm getting 581.54 hertz. So that is my second overtone. So that is it for this problem.